The gradient is the vector operator, the grad operator, this thing is called, operating on a scalar field. And when it does that, it produces a vector of the individual components. The divergence is the gradient operator operating on a vector field in such a way that the output is a scalar, a single number. So when you take div dot q, then you get partial x qx plus partial y qy plus partial z qz, not a vector. Okay, do you see how that things are slightly, significantly different? Yeah.
Is grad t a vector field as well?
Yes. So this is yes. Grad t is a vector field. Yes, it behaves exactly like a vector field. Yes. Yeah. So if I replace grad q by just minus lambda grad t, then I have this thing. Okay. Now, what this guy is called, grad squared is another operator from vector calculus. It's called a Laplacian. And it is just this thing. Okay? So now, this is a dot product of two vector operators. So it shouldn't take too much imagination to realize that what that means is just this guy. Okay, so it's just the dot product, again, same as any other vector dot product, but it's the dot product of two operators, the dot product of the vector partial x, partial y, partial z with itself. So it gives you a scalar object, which is the sum of the second derivatives. Okay. So if we're going to write this out, then grad squared t would just be the second derivative of t with respect to x, plus second derivative of t with respect to y, plus second derivative of t with respect to z. Okay. So if we stick all those things together, then we get the equation that I was trying to get to, that the partial derivative of the temperature with respect to time is just some object, some number, times the Laplacian of the temperature. Okay? And this quantity dt is the thermal conductivity divided basically by heat capacity mass density, and this thing is called the thermal diffusivity. Thermal diffusivity or thermal diffusion coefficient. So it has the units of a diffusion coefficient. It's just meters squared per second. Okay? So basically any particular material, whether it's solid or liquid, it'll have a thermal diffusivity, and you can usually either look up the thermal diffusivity itself, or you can look up the thermal conductivity and the heat capacity and the mass density and calculate it. But usually you can find thermal diffusivity directly.
Is that always going to be a constant, or it might change?
Good question. So thermal diffusivity depends on the density and temperature. And so what we're going to be assuming here is that the temperature changes are sufficiently small that the thermal diffusivity is constant, but it is not in general a constant. You're right. Okay, but we're going to keep it. We're going to do that to keep it simple. Simple. So this thing is called a diffusion equation. I expect you've seen that before, maybe not written exactly like that, but something very similar, because it's one of the fundamental equations for heat and mass transport. Yeah. Now you'll know that there are additional complications, because in liquid systems you can also have convective heat transfer, and in many cases the convective heat transfer is actually the dominant one. So this is not all there is to the story. But what I want to do here is to introduce you really to partial differential equations. So what we're going to do is to take this as our sort of prototype equation and learn how to solve that in a couple of different cases. So the first case I want to look at is when there's only one space dimension. So we're going to assume that t is the same in y and z directions. So t is just a function of a single coordinate and time. Okay? So what sort of problem looks like that? So here's one. So imagine I got a thin copper rod. It's 30 centimeters long. And it's at room temperature. Which will take to be 25 degrees C. And then one end is placed in boiling water. So in other words, it means that that end is 100 degrees C. And what we were going to learn how to do is how to plot the temperature profile in the bar at 5 seconds, 25 seconds, and at 100 seconds. Okay? So the idea is here's the bar. It starts off, the whole thing's at 25 degrees. And then instantaneously, I make this end 100 degrees. Okay? Now, what's going to happen is the heat will propagate down the bar so that there will be a temperature profile in the bar. Yeah? So what do we know? We know that if I was to plot this between 0 and 30 centimeters, at t equals 0, it would look like this at 25 degrees. The temperature would be constant everywhere in the bar. And then right at that time, I heat one end of the bar. So what we know if we wait a while is that we would have a steady solution. So as time goes to infinity, then our temperature will be the solution of the equation, this guy, which you've definitely seen in elementary transport. Because if we wait long enough, we come to steady state, it means that the temperature isn't changing in time. So this guy would be 0. And then in that case, the solution of that is just t is 25 plus I think 2.5x, right? So that will be the solution at very long times. So at x equals 0, it's 25 degrees. At x equals 30 centimeters, it's 25 plus 75 is 100. So I'm satisfying the boundary conditions at both ends. And we know, since it has to be a solution of this differential equation, that it can only vary linearly between the two ends. So that has to be what the temperature field looks like. Yeah, okay. So that's what happens at the end. So at the end, it would look like this. But what we want to find out is, okay, what happens between the beginning and the end? What does the temperature profile look like at those intermediate times? Did you solve this problem in transport with time-dependent transport?
Yeah.
So you did it by separation of variables, right? Yeah, okay. So that's not what we're going to do. That's not what we're going to do here. We're going to solve it by essentially reducing it into a linear system of equations. The advantage of doing it the way I'm going to show you, it almost inevitably involves using the computer, but it's more flexible than separation of variables. There's lots of equations that you can't solve in that way, which can be solved by essentially using finite differences. So I introduced you last week to the idea of finite differences as a way of solving boundary value problems. So we're going to come back to that same notion this week, and we're going to use it first off to solve this kind of partial differential equation. Oh, there's one other thing we need to know, which is that for copper, dt is 1.15 centimeters squared per second, okay? So you need to know the thermal diffusivity in order to put a proper time scale on what's going to happen, okay? So the idea that we're going to use then is finite differences. And so what we're going to do is to essentially divide the domain up into little chunks, okay? And we're going to calculate the fields at those individual points within the system. So we're going to take the bar and divide it up into little domains. So this would be x equals 0. This will be x equals 30. And here we have t equals 25. And here we have t equals 100. And what we need, we know both of those things because we know the boundary conditions tell us that t is 25 at this end, and they tell us that t is 100 at the other end. But what they don't tell us, what we can't yet figure out, is what the temperature is at all those intermediate points. Okay, so that's what we want to try to find. Now, in order to use finite differences, there's two things we need to decide. What are we going to use for this distance h, the distance between each of the little segments we're going to calculate? So if you make h too big, the solution isn't going to be very good. If you make h too small, then you'll land up exhausting all the memory in the computer, and that won't work either. So we've got to land up finding reasonable values for h. Now here we're not just solving for the temperature as a function of position, but we're solving it as a function of time. That means we also have to decide how quickly we're going to step through time, because the temperature is going to be converted to something that depends on specific positions in space, but also specific instances of time. And we're going to have to decide how long we want between each instance. Okay? So I'm going to start off, when I get to actually solving it, I'm going to start off by trying something that seems to me to be fairly sensible. We'll try h is 1 centimeter. It's a 30 centimeter long bar. What I'm saying is I'm going to divide it up into 30 segments. So what I'm assuming is that there isn't too much variation between those two segments. It doesn't really matter because we can always go back and increase the number of segments if we haven't taken enough. Okay? And I'm going to assume a time step of 1 second. Okay, because I was asked to calculate things at 5, 25, and 100 seconds, so it seems like a reasonable kind of guess as a starting time scale. Okay. So once again, this is the actual partial differential equation that we're trying to solve. And in this case, the temperature is a function of position and time. So in order to use finite differences, I have to discretize both space and time. So I'm going to discretize time by making it into some integer multiples of the time step, okay? So delta t is the time step. So in the case that I'm going to use, we're going to start with 1 second. So that means, in other words, I'm going to calculate the temperature field at time equals 0, at time equals 1 second, 2 seconds, 3 seconds, 4 seconds, 5 seconds as I step forward in time. Okay. And then space will be some integer multiple of the step size h, which in this case is 1 centimeter. So m will be 0, 1, 2, up to 30. Okay? So I'm going to calculate my temperature at those discrete times at each of those discrete points. Okay? And then what I'm hoping is that I then have enough information from this to be able to reconstruct and make a reasonable plot of the temperature field. We won't know that until we've actually solved the problem, so we have to essentially try and see what's happening and then maybe go back if it's not quite what we wanted. So then, instead of having t being a function of those two guys, what we have now is a set of just numbers with these indices n and n. So n would be 0, 1, up to n, and those would be the discrete time steps. And if I have a time step of 1, then n would have to be 100 in order to get to 100 seconds. So I'd imagine that I'd have 101 different values of n, starting at 0 and landing at 100. And that for m, I'd have to start at 0 so those are the space points. And in my first try, m would be 30. Okay? So I'd have 31 space points distributed evenly along the bar, and I'd have 101 different time steps. And I'd want to find what the temperature is at all of those points and at all of those times. So just like last week, what I'm going to do is replace the differential operators with differences. So if you remember last week, that's how we solved boundary value problems. Instead of having a differential equation, we essentially replaced the differential operator with differences, and then we just got algebraic equations. So let's see if we do the same thing again. So what I want to do is to replace dt dx at a time t and a space point x. And I know I flipped the notation around, but that's because of the order I chose these guys. So that will be t at the time t plus delta t, and at the space point x, minus the temperature at t and space point x, divided by delta t. And there will be errors in that of order delta t squared. And that just looks like an Euler update, right? We've just replaced the first derivative with the guy at a slightly later time minus the guy at the current time divided by the time step. And that's exactly the same idea as in our simplest method of solving an ordinary differential equation, which was to replace the partial derivative with this 2-point difference. Yeah. So that, you see, it allows us on the left-hand side to go in and plug in an approximate equation that gets rid of the partial derivative with respect to t and just replaces it with the temperature field itself. And then we need to do the same thing for the space derivative. And in that case, again, it's the same formula that we used for the second derivative that we derived last time.